This is section 6.2, multiplying matrices. Your I can statement for this half of the section, I can multiply matrices. So the three basic matrix operations are matrix addition, scalar multiplication, and matrix multiplication. We discussed matrix addition and scalar multiplication in section 06. Remember, with matrix addition, you just add the values that are in the same location. For scalar multiplication, you just take the value and you multiply it by each value inside the matrix. To multiply matrix A by matrix B, the number of columns in A must equal the number of rows in matrix B. So this means if the dimensions of matrix A are 3 by 2 and matrix B are 2 by 4, these two numbers that are in the middle have to match. The number of columns in A must match the number of rows in B. And if we do multiply these two matrices, you'll end up with matrix C, and the dimensions for matrix C will just be the values that are left over. So this will be a 3 by 4 matrix when you're done. Now if A is an M by R matrix and B is an R by N matrix, like I said, we'll end up with a M by N matrix when we're done. But when you multiply, to find the first value of our product, it's in the first row and first column. So we're going to take the values from the first row of matrix A and multiply it by the first column of matrix B. So we'll do A11 times B11 plus A12 times B12 plus A13 times B13. And the answer of that will go into C11. Now to find C21, this is in the second row, but it's still the first column. So we would do A21 times B11, A20 plus A22 plus B21 times B21 plus A23 times B31, and that would tell us what would go into C21 because those are from the first row of matrix A and the second row of matrix A, first row column of matrix B. So if we take a look at this example, first of all, A is a 2 by 2 matrix. There's 2 rows and 2 columns. Matrix B is a 2 by 3 matrix. Because we have a 2 here and a 2 here, we are allowed to multiply these, and you will end up with a 2 by 3 matrix when you're done. So we're going to have 2 rows and 3 columns. To go for the first one, to find our C11, we're going to do the first column, the first row times the first column. So we will have 3 times -2 plus -1 times 3. And that'll be your C11. To find C12, we'll still take the first row, but we'll multiply it by the second column. So this will be 3 times 0 plus -1 times 5. Then to find our C13, it'll still be the first row, but it'll be the third column. So 3 times 6 plus -1 times 1. Now we'll move down and start the second row. So it'll be the second row times the first column to get your C21. So we'll have 4 times -2 plus 0 times 3. Next we'll do second row, second column to get our C22. And we'll have 4 times 0 plus 0 times 5. And last we will do the second row, third column to get our C23. And this will be 4 times 6 plus 0 times 1. So if we do these multiplications, 3 times negative 2 is negative 6, plus negative 1 times 3 is negative 3. So negative 6 plus negative 3 gives us a negative 9. 3 times 0 is 0, plus negative 5 will give us negative 5. 3 times 6 is 18, plus a negative 1 gives us 17. 4 times negative 2 is negative 8. Negative 8 plus 0 is negative 8. And then we have 0 plus 0, which gives us 0. Then we have 24 plus 0, which is 24. So our final solution will look like this. Now the ones on your homework, you do need to show your work and do these by hand. But if you want to check your work when you're done, you can multiply the matrices on your calculator to make sure you got the correct answer. If we try another one of these, matrix A is a 2 by 2 matrix. Matrix B is a 2 by 3 matrix again. So once again, we can multiply these. We start with the first row and the first column. So 3 times negative 2 plus negative 1 times 3. This is the exact same one as the previous example, so we're just going to go ahead and skip this one. Oh, this one wants B times A. That's the difference on this one. So if we do B times A this time, if we look at the dimensions for B, B is a 2 by 3, and you want to multiply that by matrix A, which is a 2 by 2. Now these dimensions do not match, so this one is not possible. So you do need to make sure you pay attention to the order of multiplication, because the order will make a difference. For any matrices A, B, and C, for which the matrix product is defined in any scalar k, the following properties are true. We do have the associative property of multiplication of matrices. So that means if I have matrix A times matrix B times matrix C, you can actually switch and multiply B and C together first and then multiply A. The associative property of scalar multiplication, you can do K times A times B, so you can multiply matrix A and B together first and then multiply by the scalar. Or you can multiply the scalar by A and then multiply by matrix B. Or you can do your scalar times matrix B and then multiply by matrix A. Left distributive property says you can distribute the value first and then add the matrices, or you can add the matrices and then distribute. And the right distributive property says the same thing, but it's on the right. The percent of voters of different ages who were registered as Democratic, Republican, or Independents in a recent city election are shown. Use this information to determine whether there were more male voters registered as Democrats than there were female voters registered as Republicans. So when we multiply these, we have our matrix. So we would have here and here would be matrix A. We have Democrat, Republican, and Independent. And this is a 3 by 4 matrix. We're going to multiply this by matrix B, which is a 4 by 2 matrix. Because these values are the same, we are able to multiply, and we're done. You're going to end up with a 3 by 2 matrix. That 3 by 2 matrix will be Democrat, Republican, and Independent, because those are the values that we're looking at for our 3. Our 2 are female and male. Now because these are larger problems, you can go ahead and use your calculator for these type of problems. In your resulting matrix, would look like this. So our question was, are there more male voters who are Democrats than there are female voters who are Republicans? So male Democrats, after you multiply, you'll see there's a total of 34,275 male Democrats that are registered. Female Republicans, we have 33,650. So yes, there are more male Democrats that are registered than female Republicans. You know that multiplicative identity for real numbers is 1, because any real number a, if we have a times 1, you'll still end up with a. So as long as you multiply something by the multiplicative identity, you end up with itself. And an identity matrix is a matrix of order n, denoted I sub n, and this will always be an n by n matrix, so it has to be a square matrix, consisting of all ones on its main diagonal from upper left to lower right, and zeros for all the other elements. So this is the identity matrix for a 4 by 4 matrix. You're going to have the ones on the diagonal, and you're going to have zeros everywhere else. If we wanted a 2 by 2 matrix, this would just look like this. So we need to write a system of equations as a matrix equation AX equals B, then use Gauss-Jordan elimination on the augmented matrix to solve the system. So we used augmented matrices in section 6.1. We're going to do the same concept here. So we have matrix A augmented to matrix B. Now what we really want to find is matrix A times matrix X is equal to matrix B. So what we're really looking for is that -1, 1, -2, -2, 3, and -4, 3, -4, and 7, matrix A times matrix X, which is our x sub 1, x sub 2, x sub 3, is equal to matrix B. And we want to find the values of our x values to make this true. Well, we know that the identity matrix times any matrix will just equal the second matrix itself. When we augment, we end up in reduced row echelon form. We end up with the diagonals of ones and zeros everywhere else. So that does end up with the identity matrix. So one way to solve this is to augment to do your reduced row echelon form, and then we will be left with our matrix for X. So right now, this is matrix A augmented with matrix B. If we do our reduced row echelon form, then we will be left with 1, 0, 0, 0, 1, 0, 0, 0, 1, and -13, 1, and 6. Now by doing the reduced row echelon form, now we ended up with the identity matrix, and this will be our matrix X. And the identity times matrix X will always equal itself. So if we put the values in, that means these are our X values. So we know our x sub 1 is equal to -13, our x sub 2 is equal to 1, and our x sub 3 is equal to 6. Or we can say that matrix X is equal to -13, 1, and 6.